So I'm going to prove Favard's theorem following Aigner's book in this section 7.1. It's a characterization of all orthogonal polynomials, all families of orthogonal polynomials.
I see it's a very short proof.
Yeah, in terms of, it's just one section in terms of two sets of parameters. So these parameters are given by usually sigma and tau. And these could be any complex numbers. Uh, and we assume that these t's are not zero for all q. And then you define a triangle of numbers. These are maybe called Catalan triangles. So the first row is the first element is 1, and then a and k is 0 for all k greater than 0. A0k, sorry, is 0 for all k greater than 0. And each row is defined in terms of the previous row by a recurrence relation like this. an minus 1 k minus 1 plus sk an minus 1 k plus tk plus 1 an minus 1 k plus 1. It's I find it helpful to visualize this. Um, uh, uh,
TK, I suppose.
no, it's tk plus 1.
T
So this
A1.
starts, yeah, I'll draw the picture.
Yeah.
So the s's start with 0 and the t start with 1. Okay, and so let me just draw the picture. There are three kinds of, so you have this triangle, and you have three kinds of edges. So you have edges going in this direction. These have weight 1. Then you have edges going downwards. These have weight s, given by s, various s's. So these have weight s0, and then these have weight s1. These have weight s2, and so on. And then you have edges going diagonally in the opposite direction, and these have weight t. So these have weight t1, these have weight t2. And what you're saying is that to arrive at the value of a certain vertex, you take all the in edges and you take those values and multiply them by the weights of those edges. So in other words, what you get is that a and k.
Just to clarify, you're not drawing the other red ones because those numbers are still on top of it. So on the upper triangle, it's
Yeah. So there, so here everything is 0 in this region,
yeah. So
and so there's no need to worry about it. So a and k is another way of thinking about it is in terms of paths. So it's a sum over all paths gamma from the vertex. This is the vertex 0, 0, and from the vertex 0, 0 to the vertex nk, we talk about directed paths of the weight of gamma, where the weight of a path is the product of the weights of um, its of the edges that form the path. Okay, so the blue edges have weight 1, so I've not written them at all. So W
oh,
gamma,
this is set up for a that is that SLVM will stick.
yeah, there is that too. as such, this will lead to, if the s's are all 0, then this will lead to counting of dict paths.
But it seems that there are multiple paths and they might have the same weight, right? Or they might have different weight.
Yeah, so whatever it is, you add all the weights. So you enumerate over all paths. So if there are multiple
Okay,
paths
okay.
with the
You
same
consider
weight,
all the paths.
yeah. So the sum is over all paths. And another piece of notation is that we will call this, we will think of this as an infinite matrix. And we will also, since it's completely determined by sigma and tau, we will call this matrix A sigma comma tau.
But I just see that all the paths have the same weight. Is that
What
not
do you
right?
mean all the paths are the same weight?
Like if you start from 0, 0, and if you go, what is the row
So
number?
let's
Then
look at what we get here. So this thing is 1. Okay, so here you will get S0. There's only one path,
uh,
right?
yeah,
Here,
in
what
this,
will you
yeah,
get?
yeah.
You'll get S0 squared plus T1. Okay, there are two
Okay,
paths
okay.
from 0, 0 to here. One is
If
S.
you go to the next column, then you will
Yeah.
see that the paths.
So here you'll get S0 cubed plus, then you have this path T1 S0, and then you have a path, yeah. So yeah, that's it, right? S0, T1. Oh, and then you have
S1,
this
S1 T1.
S1,
Down and
S0, T1, S1. Oh, yeah, this one,
S1 T1.
S1.
Yes.
Okay, so they don't all have the same weight.
Okay, but on the second column, if you go,
Yeah, here.
yeah, 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 and one blue and one green, right? Means each path consists of one blue and one green. Even if you
Okay.
go the, yeah.
Yeah, so
Yeah,
this
but
path,
that is the green ones are not the same. I mean, depends on the color. It's S0 T1 plus S1.
yeah.
Oh, I see. Right, right, right. Yeah,
So
that's the
the S's are
confusion.
different.
Thanks. Yeah, yeah,
And
thanks.
so
Yeah,
the red ones are all not the same also. They are, the red ones differ in the columns in which they appear.
Yeah.
yeah, yeah, correct. Yes, correct. Yes.
Okay, and let me just point out one interesting special case. What is A uh, K K minus 1? So firstly, what is A K K? A K K is 1,
One.
right? Because you just told it. But what is A K K minus 1?
That should be S0 plus S1 plus.
So this is going to be, so if you look at this K equals 1, then it is just S0. If you look at K equals 2, it is either you can go like
S0,
this or
S0
you can go
T1
like
plus
this.
S1.
Yeah, so this will be S0 plus all the way up to SK.
Amri, eh,
Yeah, maybe I should also.
no. There is a T also, right?
No, there is
No,
no
there is
T.
no T. There is no
Yeah,
T.
yeah,
Ah,
yeah.
okay. There is no T. Correct. There is no T.
So let me record also this fact that A KK is equal to 1. The diagonal entries of this matrix are 1. And just below the diagonal are these things. And from these, you can recover the S's. And yeah, and another common case is when all the S's are 0. When all the S's are 0, then what you see is that this diagram breaks up into two connected components. That is Aij, where I plus j is even, and Aij, where I plus j is odd. Because the green and red edge, no, the blue and red edges only connect uh, nodes with the same uh, parity of the sum. And so in that case, if you start with this condition, half these things will be completely 0. So if the S is are 0, then half the entries will be 0. The most important example is probably the Catalan, the one which gives rise to the sequence of Catalan numbers. So you take Sn equals 0 for all n greater than or equal to 0, Pn equals 1 for all n greater than or equal to 1. Then what we get is A2n is equal to the number of Dick paths. Let me explain what a Dick path is of length 2n, which is the nth Catalan number.
Amri, how to visualize this thing that Sn is 0 in the picture?
Then these green things are gone. So let's just draw this thing in this special case. Okay,
And
so
all things are blue lines now.
no, there are also red lines, but their weights are one.
Yeah, weight is 1, so can we consider that as all blue?
Well, no, let's just think of them as red lines
Okay.
with weight 1. So let's just draw this thing, and this is the original Catalan triangle. So we start with 1, and this will be 0, but here we will be 1, because what we have to do is, now the rule is that if you have a node, you have to take the sum of this plus this. Right, when you have blue and red both having weight 1. So so maybe this is red. So what you have is this, and you have this. So this is could be this. So it's a bit like Pascal's triangle, slightly modified. And on the diagonal, you will always have 1. So now we will have 1, 0, 1, and let's go a little further. 0, 2, 0, 1, 2, 0, 3, 0, 1, 0, 5, 0. So you see the zeros are going to be there everywhere, like in a chessboard, the white squares, and 4, 0, 1. So there's a lot of empty space here. And then 5, 0, 9,
So all even diagonals are 0.
5. Odd diagonals are 0. 0, 0 is positive. This is 0, 1. So you start counting with 0 here.
Okay, yeah, that's then fine, yeah.
Okay, so yeah. So here we have 5 plus 9 is 14. And here again we have 14, 0, 6, 0, 1. Just do one last row. So here we have 14, 0, 28, 0, 20, 0, 7. So you see some patterns here. So you have ones in this diagonal, then you have 1, 2, 3, 4, 5, 6, 7 on this diagonal. But what is interesting is along this column, you have the Catalan numbers, namely 1, 1, 2, 5, 14, and so on. Okay, so those are the Catalan numbers. And in general, we will write Bn to be an0, depending on general sigma and tau, and we will call these generalized Catalan numbers. So that's Bn. And you can ask, what is Bn? So if you look at this picture where all the weights are 1, you can ask, okay, so what does this 5 signify? This 5 signifies that there are 5 paths from here to here, which are going always downward. So this is the first path, maybe, right? Path number 1. But then what you can do is you can change it here, path number 2, right? So I just shifted this. The other thing you can do is you can make it path number 2, and then what you can do is path number 4, and what was path number 5? I guess hmm, so anyway, there must be one more path. So I guess there should be 3 paths through this point. So I guess the other path through this point will be this. This I had not done. So these paths, so what are these paths? They are always going either southeast or southwest along this lattice, and they remain to the right of the y-axis. So these are called Dick paths. And what we're talking about are Dick paths of length 2n, that's the nth Catalan number. And there are many other characterizations of Catalan numbers. So anyway, so this is the Catalan triangle, and when you apply general parameters sigma and tau, you get what are called generalized Catalan triangles. And if you look at the exercises in Aigner's book, you'll see that there are lots of interesting sequences that you can get. So yeah, so here's the main thing that will make all this related to uh, orthogonal polynomials and everything. So now we'll think of things as matrices. So I will write A as
Did you say, Amri, that there is a characterization of these generalized Catalan numbers?
so they depend on the parameter sigma and tau.
Yeah, I understand. But instead of, is there some? I'm confused. Okay, whether is there some other characterization?
Well, I mean, most generally, what you can do is you can write down these polynomials in the S's and T's.
Yeah, I know,
Yeah.
but still, uh, in terms of the numbers and themselves.
Yeah. So there is one. So I'll come to that in a minute. It has to do with the determinants of Hankel matrices.
This is what you said. Okay, last
Yeah.
time. You said that last time. Yes, yes.
So that's
Yeah, that is the
beautiful
B0s,
result.
B1s.
Yeah.
Okay,
Yeah.
okay.
Yeah.
I
And that whole thing becomes clear once we make the connection with orthogonal polynomials. So in fact, that's a very important point. So let's. I want to turn these kind of calculations into matrix multiplications. So I'll say A as the matrix A and K. These are infinity by infinity matrices, but if you think about it a little bit, it's possible to multiply two lower triangular infinity by infinity matrices. They're infinite in one direction, only in the positive direction in each index. So I'll take this. T will be the matrix capital T0, capital T1, capital T2, where capital T0 is defined to be 1, capital Ti is defined to be the product of T1 up to Ti. So these are products of the T's, the matrix of products of the T's. And H is the Hankel matrix, and this is the matrix B0, B1, B1. So this only depends on the Catalan numbers. And we'll see how these things carry. And you can think of this as an infinite matrix. And so the ijth entry is bi plus j. So it's called a Hankel. And the main computation here is the following, that A transpose TA is equal to H. So what this means, if you think about it, what this says is that we need to prove that. So you take the m comma nth entry of this Hankel matrix, it's Bm plus 1. And this should be summation Amk Ank times Tk for all n. So this matrix identity is equivalent to this summation over. And these are finite sums. Okay, this is the reason you can multiply these local triangular. So these are finite sums because once k exceeds the minimum of m and n, there will be 0 terms. So to prove this, we'll induct on m. So the base case is for m equals 0, what you get is bm, bn.
Oh, sorry, only
Yeah.
So this was like h m comma n, right? H sub n comma n.
Yeah.
But you're starting with 0, suppose. Okay, doesn't matter.
Yeah.
So this would be A transpose M something T
A
something,
transpose T A.
A transpose T A. So A transpose would be A transpose M. So it shouldn't assume
Oh,
that
sorry.
AM.
Let's put it. I think I made a mistake. It should be AT A transpose.
Okay. So A M K, that is okay, and then T sub A H and okay. Thank you.
Yeah. Thanks for the correction. That was a mistake. So this is what it is. So let's look at what happens when you put m equals 0. Then we get bn is equal to, and now amk is 1 if k is 0 and 0 otherwise. So all we get is a and 0 and then t0, which is 1. But this is the definition of bn. So this is okay. bn was defined as the entry of the first column. And now we do the induction, and so now summation. So for m greater than 0, we have, so let's take this sum. So let's now use the inductive definition of amk. And so what we get is summation am minus 1 k minus 1 plus sk am minus 1 k plus tk plus 1 am minus 1 k plus 1. And this is multiplied by ank tk. And now let's so here it's assumed that if k is less than 0 or something, then these indices are 0, usual kind of conventions that are used. And now what we'll do is we will try to make this we will try to make this m common and vary the n. So we will collect the terms corresponding to am minus 1. So what is the coefficient of am minus 1k? So it is an k plus 1. But then we'll have a tk plus 1 plus sk ank tk plus
Yeah, this the middle term that you're doing, AM minus 1K, I lost.
I'm taking the contribution of each of these. So now we can think of this as 3 sums.
Yeah.
And then I will reindex the k for each of those sums accordingly. So the first sum would just be am minus 1, k minus 1, a and k. So if I reindex, that will become am minus 1 k, a and k plus 1, tk. Plus 1, and then this becomes this, and the last one becomes tk times an k minus 1 tk minus. So just re-indexing each of those things separately. But now, if you think about it, this can be rewritten as am minus 1k. I'll take out tk common here. And so what I'll get is an k plus 1. And here I'll get
Yeah,
tk plus
can
1.
we just 1 second? This last term, um, you get tk and minus 1.
tk
minus
is,
1, got it.
yeah.
Thanks.
So this will collectively become tk. This little tk times capital Tk minus 1 will become capital Tk.
Yeah.
And beautifully, that is
Yeah.
just an plus 1.
Why there is small tk plus 1?
Yeah.
Yeah.
Because this is capital Tk plus 1. So what is capital Tk plus 1? It is capital Tk times small tk plus 1. And I have
Okay,
taken out
okay.
capital Tk here.
Okay.
And these two just give me Tk. So
Right.
there's no. An plus 1 k. And that's now by induction, we know that this is equal to the m minus n plus m minus 1 plus n plus 1. Because we are assuming that this is true for all n for a given m. Okay, so by induction. That's it. So the proof is done. Is this okay?
Yeah, good.
Yeah.
Okay, so we have a different now point of view of this Catalan triangle, namely this equation. And the next proposition will show that these two ways of looking at it are equivalent. That is, if you have what we've seen is that if you have a equal coming from parameter sigma and tau, then it is satisfies this kind of equation. And what we'll see is the converse. If you have a triangle which satisfies an equation of this kind, then we can find parameters sigma and tau such that it comes from those parameters. So, so what we have is A is equal to A sigma tau for some sigma tau as above, which means that, you know, sigmas S0, S1, S2, tau is T1, T2, T3, and these are non-zero. If and only if there exists a diagonal matrix T, which is of the form T0, T1, with T0 equal to 1, Tk not equal to 0 for all k, and yeah,
Not this tk is equal to this related to tau, like that, like so.
it will end up
That
being,
is
yeah,
okay. That is
yeah, and a Hankel matrix.
Sorry, I forgot what is sigma and tau.
So sigma and tau are what we had right at the beginning. These parameters,
Oh,
SS
okay.
and T,
A0
these
and okay,
weights
okay,
of the
okay.
edges.
And A sigma of tau means that this
It
matrix.
comes from, yeah. So what we are saying is that this equation and a Hankel matrix H equals B m plus n for some sequence any sequence, such that A P A transpose is equal to H. So what we're saying is that all Catalan triangles come from some sequence of T's and some sequence of generalized Catalan numbers. If where you have this relation, so this relation is necessary. And so Raghavan's question of when you have this, when a sequence is a generalized Catalan numbers comes from whether or not this Hankel matrix has such a factorization or not. It gets translated into another question. Okay, so this is the proposition, and we've already proved,
just addendum is, if this is so, then the H is given by the TIs are given by the
if you
product.
can factorize H.
Okay.
And then we'll see that you can do that if and only if the finite principal submatrices of this have non-zero determinant. So that's going to be the fine. So proof, already we have proved this part, right? We started with A sigma tau and we proved this. This Ti turned out to be the product of T1, T2, Ti. And the Hankel matrix turned out to be this. So for the converse,
So you have
So,
to show that these TIs are products of some capital TKs are products of some T1.
whenever you have such a sequence of non-zero entries, you can always write them as products. So that's not a difficult, right? You just define Ti to be Ti divided by Ti minus 1 for all I greater than N. So that's not an issue.
But how do we know that they are positive?
Nobody said they are positive. We only said they are non-zero.
Non-zero.
So this theory is completely algebraic. They are complex numbers, in fact. So there's no questions of positivity here. But I guess positivity questions do come about, but not in this what I'm going to explain today. So yeah. So for the converse, suppose we have this equation, right? So that equation, I'll write it in the summation form. AMK ANK TK is equal to B M plus I for all M. Then already what we know is that Bn equals ANZ, right? Just taking M equals Z. So that's so the B is determined by rather the AN0 is completely determined by the sequence of B's. So what I'm going to show is that A is uniquely determined by this factorization. So what we also have is that an plus 1 plus I comma 0, well, this is b n plus 1 plus I. This is an plus 1 0 ai 0 t 0 plus an plus 1 I ti. That's what this sum becomes when I take m to be n plus 1 and n to be I, right, in this sum. And this allows us to solve for an plus 1 I in terms of an plus 1 0, an plus 1 1 up to an plus 1 I. all these other terms.
One second only. This second, so you are assuming the AIs to be upper charge is lower factor.
Yeah.
You need to write that as well.
Yeah. Okay. Yeah. Yeah, I need to assume that A upper track. Hmm. Yeah, thanks. That's needed. So that's definitely needed. Okay, so and it doesn't matter much what this is. The point is you can always solve for A. So given this situation, you can always solve for A and find your matrix A, and then you can derive you can obtain sigma and tau also using this. So Ti will be Ti by Ti minus 1 for all I greater than 0. S Si will be A k plus 1. What? K minus 1, right? Sk be A k minus 1 minus A k minus 1. Sorry, A k plus 1 k minus. So what we had observed earlier that uh, Akk minus 1 minus Ak minus 1 k minus 2 is Sk. Do I have it? Is this right or is this so A? This is A2. So I think this should be K plus 1. So what we have here is A K plus 1 K minus K minus 1. Then you take the matrix A equals A sigma tau, and then clearly that satisfies this equation by our earlier calculation. Because in this now A T A transpose is equal to H. Because we constructed it using I mean this H is determined by just this condition, right, by the entries of it. So this proves this proposition. I hope this is okay.
So in the expression of a n plus 1 I, which is Ti inverse of that thing
Yeah.
in the bracket, there will be a Aii inverse also.
Oh, maybe, yeah. But AII is 1, so that's why.
Ai.
Yeah. It's not, yeah, so that's true, but it's not very important what the exact form of this is, though I think this is correct, right? But the important point is that you can solve for it uniquely.
No, but this AII equal to 1 is part of the hypothesis, or is it followed?
Okay.
You want to put it as part of the hypothesis?
Oh yeah, that's a good question. I think you will find it, yeah, so inductively probably. Yeah.
So you said before something is
So, okay, let's just put it here. Okay, so
no, I didn't get. I mean, didn't you prove earlier AKK is one or something from that?
that is if I know that the left hand side, in the situation of the left hand side. In the situation of the right hand side, I'm saying that A is uniquely determined by this. On the other hand, A sigma tau satisfies this. So therefore, A must be A sigma tau. That's the argument. So in the situation of the left-hand side, we know that AKK is equal to 1. In the situation of the right-hand side, we only know this factorization and we have to deduce everything else.
So you are saying it follows that AI equals 1.
Everything follows, yeah, by the unit.
Okay, got it.
So that's the main proposition, and that's probably the now we are done with all the difficult calculations, and now it's just okay. So now let me get to the
I
construction
mean,
of
at the end of the day, it's a triviality. I mean, it's just some matrix.
yeah, it's
Yeah,
completely elementary.
it's complicated. Yeah, I mean, it's just seeing it from a different point of view. That's
Yeah.
all.
So now let's, so the non-triviality lies in sort of the realization that, yeah. So let's let U equal to A inverse. Okay, maybe this is another little calculation that we have to do. This is actually exercise in Aigner's book. So let's call this matrix U and K. This will again be a lower triangular matrix with ones on the diagonal. So then what we have is this also satisfies a recurrence relation U0, 0 equal to 1. U0k equals 0 for all k greater than 0. That's just saying that it's triangular. And un plus 1k can be written as unk minus 1 plus sn, no, minus sn unk minus tn un minus 1k for all n greater than 0. So U is determined by different recurrence relation. Note that here we have Sn and Tn, not Tn plus 1. And yeah, mm. and notice that yeah, there's some. Okay, so this is to be compared with. Let me just copy this out. Basically, what we are saying is that these two sets are equivalent. Huh? Oops, how do I these sets? Okay, let me just.
Probably you have to resize there, then best.
Oh, there.
Ah, no, it's okay.
Okay, so this is the original one, and this is the new one. So, so the signs have changed, and there's a change of index here. The index now depends on n, whereas there it depended on k. And the proof of this is fairly straightforward. It is. I just did it using matrices to define J to be the infinite matrix 0, 1. Okay, now I'm going outside my upper triangular, lower triangular matrices. So you have to be a little careful. So this is some sort of Jordan block. S is the matrix S0, 1, T1, S1, 1, 0, T2, S2, 1, and so on. So the next row will be 0, 0, P3, S3, 1. So this is another infinite matrix, not quite lower triangular. But the point is that there are only uh, finitely many entries in each row to the right. Anyway, you have to check that matrix multiplication makes sense. And what we have is that JA equals AS. That's what this original relation means, that JA is equal to AS. And this is the same as UJ. Multiply on the left and right by U, you will get UJ is equal to SU. And SU, and that this is equivalent to, so this is equivalent to this is equivalent to this thing, and this is equivalent to this thing. So these and these two are clearly equivalent. So this is equivalent.
Neat.
Okay. But you could probably write it out in terms of indices and prove it as well by induction or something. Anyway, so that's the thing, and now we can define what will become orthogonal polynomial sequences. Let P and X equal to summation k greater than or equal to 0, u n k x to the power k. Then one consequence of this result is that just this identity is that firstly, uh, uh, one is that P0x is just 1, right? That's because of this U00 is 1 and U0k is 0. And secondly, uh, Pn plus 1x. So this will come from this in terms of Pnx. So what we are saying is that it is x minus Sn. So here there's a shift in the k index, so that I'm taking care of by multiplying by x, Pnx. Minus Tn, and here there's a un minus 1, so I should put un minus 1. So that's what these relations become in terms of the orthogonal polynomials. This one can be rewritten as x Pnx is equal to Pn minus 1x plus Sn Pnx plus Pn plus 1x. This is the form that we see in Stanton's paper. So you take Pnx and multiply it by x. It has expansion which involves only Pn plus 1 and Pn minus 1. So that's the observations about this. And now let me define an orthogonal polynomial sequence.
So, so in the previous definition, what you were defining?
I'm
P
defining a sequence of polynomials given
and
by
okay,
certain relations. So
yes, okay,
this is now dependent on sigma and tau.
okay. This is the definition of Pn.
Yeah,
Means your
based
function.
on sigma and tau.
Okay,
Now we have another definition of orthogonal polynomial sequences, which depends on an inner product, or
okay.
rather
Now
on a
you will say
bilinear
then
form.
these two are
And
equivalent of each
Favard's
other.
theorem says that these two characterizations are equivalent. So let me make
Okay,
the other
sure.
definition. Uh, so, so a sequence P and X, a sequence of polynomials with complex coefficients is said to be an orthogonal polynomial sequence. we'll call OPS if firstly Pn x is monic of degree n for all n. This is n greater than or equal to 0. And secondly, there exists a linear functional L, just C linear, such that L of PMX, PNX is equal to, well, I can write it using chronicle delta Mn for all n greater than or equal to 0 for some, and here we insist that these lambda n's are non-zero and lambda 0. We normalize the sequence so that lambda 0 is 1. Okay, so this is the usual definition of orthogonal polynomial sequence. Of course, here we are not taking any positivity thing. We are just doing an algebraic theory. Okay, so what Favard's theorem will say is that every such sequence actually arises from this construction, which depends on sigma and tau. What we've done so far is we have not even the other way around also, that given sigma and tau, we can find an L such that our Pn comes from that L. So they're both ways. So before we go to that proof, let me just prove a small lemma which relates so you can think of this as an inner product, but you should think of it as an inner product. It's really just a bilinear form. There's no positivity. Okay, so think of this as an inner product.
On the left side should be a product.
What?
L of PMX times.
Oh yeah, sorry. No. Yeah. So that's how you should think of. And so what we're saying is that these things are orthogonal with respect to this inner product. And so now lemma is that we can characterize this in a slightly different way. L of x to the k Pnx equal to lambda n delta kn for all 0 less than or equal to k less than or equal to n. So now we are only assuming k is less than or equal to n, not allowing all k. And here we are allowing all m and n. So what we are saying is that Pn is orthogonal to all the monomials of degree strictly less than n.
And you need either inner product or L without comma.
Yeah. I won't use this inner product notation because it's a bit, yeah. So this and the same lambdas, if and only if these equations 1 and 2 above. So now the point is not only that, so these just have to hold for k less than or equal to n. So there's fewer. Okay.
So Pnx is orthogonal to all polynomials which has less degrees of n.
Exactly. But that is kind of clear here already, right? Because
Yeah.
Pnx is orthogonal to pkx for all k less than or equal to n, and those pk's form a basis for. So here we assume that Pnx is. Yeah, I guess that's it. Yeah, we assume we keep this assumption that lambda n is not equal to 0. So yeah. So I guess so. Let's prove that this this 1 and 2 hold implies the first condition. So proof of. So in that situation, what we have is that we can write x to the k as summation I goes from 0 to k, pki, pi, right? With pkk equal to 1, because these are monic. So if you take pk, it's x to the k plus something of degree less
Yeah.
than k, and then that spans that. And so what we get is L of x to the k, L of x to the k pnx is equal to summation pki L of, just using linearity, but that's equal to, so the only term that will survive is here is ckk, and then that will be lambda n. So that proves that. And the proof of the converse is, I guess, mm, is probably straightforward. So yeah, so I think that's pretty straightforward. Again, you do the same thing. You expand now in terms of the monomials, and you do a similar calculation. So I'll just leave it out. Okay, now we can prove Favard's theorem. So let me state the theorem carefully first. So a sequence is an OPS if and only if it arises from some sigma and tau as above. Namely,
When you say PNS is an OPS, what are you assuming about PN?
so all this. It's a sequence of complex polynomials where Pn is monic of degree n. There exist non-zero complex numbers lambda n such that.
No, that my question was on the other side, if and only if they arise as.
There exist.
One second. Okay, let me do it. It arises from sigma tau as above, where sigma tau, I guess. So the TIs are non-zero. That's all.
Yeah, so I'm saying that there exists sigma and tau such that all this stuff you do, you construct this triangle A using sigma and tau, then you construct it like.
Yeah, got it. Yeah.
So this is certainly a remarkable and surprising theorem.
So you construct A and then A inverse, which is U, and PNX is whatever. In terms
Yes,
of
exactly. So yeah. So one way we have seen, right?
The only is that.
Actually, we
Or
haven't seen
if
either way.
no, if it arises from this, then it's oh no.
No, we have not defined L, so we need to define L,
Okay.
and then we need to check. So
PNX is monic. That much we know because the U of the formula U.
So let's prove. Let's first prove this. So firstly, so we have given sigma and tau. We need to define L. So we just define L. L of x to the n is just the generalized Catalan number Pn. And now we need to check that this sequence will be orthogonal with respect to this linear functional. So now what we know is already that A T A transpose is equal to H, which is equivalent to U H U transpose is equal to T, right? Now let's write this out, what this means. This is equivalent to saying that summation UMI UNK. Now this is no longer a diagonal matrix, so we will have this, but then we will have BI plus K is equal to delta Mn times T for all Mn greater than or equal to 0. This is a sum over K greater than or equal to 0, I greater than or equal to 0, right? Uh, now, yeah. So now let's compute L of PMX PNX. And it turns out to become exactly this equation. And then we have x to the I plus k. So I can take this L out and put it here, b I plus k. But that's precisely this thing here. So this is sum over I greater than equal. If you have to add all pairs. Sorry, this is I greater than this is k greater than. This is I and but this is exactly delta mn. So the t in fact turns out to be the lambda n turns out to be
TM.
Tn. So T0 is 1. And so that proves one way. And conversely, let's prove the other way. So now we need to prove so suppose P and X equals to the K and L of X to the N equals Bn. Then the same calculation here actually shows that UHU transpose is T, because right. So what are we proving? We are proving that we have an OPS, right? So what we are assuming is that this is equal to this, but that's exactly the same as showing that. So saying that L of PMX PNX is equal to delta Mn. What was it? So what we have to show? We have to show that an OPS. Yeah. So showing that this is equivalent to showing that UH transpose is equal to T, where T is so just the same calculation. Let's look at so that's the proof of Favard's theorem, and so the proof is done, and as you can see, uh, it rests on this condition, this factorization A transpose is equal to H, and also on that proposition that we proved about all such factorizations corresponding to Catalan triangles. Okay, so that's the proof of Favard's. And let's just look at the canonical example which involves Catalan numbers. So Okay, so firstly, let's look at a slightly more general example, then where we take Sn equal to 0 for all n greater than or equal to 0, Tn equals 1 for all n greater than or equal to 1. So then this equation here that we have, where did it go? Yeah, right? So this just becomes x Pn x minus Pn minus 1x. So Pn plus 1x. And we are also subject to P0x is just 1. And there's a nice integral you can try to work out. Uh, 2 to the power 2m minus 1 divided by pi integral x to the power 2m 1 minus x squared to the power half dx. So you do this by substituting x equals sine theta. And this is an integral from, I guess, minus 1 to 1. So you substitute sine theta and it becomes integral from minus pi by 2 to pi by 2. This is equal to 1 over m plus 1 to m choose m, which is the standard Catalan number if n is equal to m and is 0 otherwise. And what this equation shows is that LF is 2 by pi integral minus 1 to 1 f of 2x 1 minus x squared.
So in the left hand, in the integral, there is no n appearing, right? In the expression.
No, n is 2m actually. Yeah, if n equals 2m. Sorry. No, this just saying, yeah. So yeah, sorry, n should be 2m. So the even moments, so these are, in probability theory, these are called moments. So you have a probability distribution, and the expected value of x is called the, it's the expected value. Expected value of x squared is called the second moment. Expected value of x cubed is called the third moment. So these are called moments. And what this formulation here is saying.
Yes, what Jyotirma meant is you want x of n plus m in the, on the left side.
There's only m here. This is 2n. N is 2n. Sorry, there's no.
So that doesn't, if since you're writing if n equal to 2m,
No, sorry. Yeah. Uh, yeah. What do I mean? Yeah, I think I should write xn here, right? I mean,
that
this is obviously 0 if n is odd.
odd. Oh, I see. Mhm.
Of course, if n
Yeah,
is odd,
there-
I don't need any of this stuff. Sorry, yeah. Sorry. So
Okay. Yeah,
this is
yeah.
obviously 0 if n is odd. If n is even, then it is given by this Catalan number.
Okay.
Also, please correct that 2 to the power n minus 1, right?
2 to the power n minus 1. Yeah. Well, the other one wasn't wrong.
Yeah.
Oh, well, it was wrong.
No, since you were writing in terms of.
Yeah.
Yeah.
So basically, I wanted to just write down the L.
Mhm.
So, yeah. So there's this 2 factor which comes out. So, yeah. And one last thing, I'll answer Raghavan's question. So, definition Bn is called Catalan sequence or generalized Catalan number sequence. If it arises from some such that Bn is equal to A M0. So that's a Catalan sequence, and the theorem is that Bn is a Catalan sequence, and this condition is surprisingly it's an open condition. It's an open dense set. If and only if determinant of Hn is not equal to 0 for all n greater than or equal to 0, where by Hn I mean the finite Hankel matrix. The n by n Hankel matrix. And the proof, well, so firstly, if Bn is a Catalan sequence, then we know that H is equal to A transpose. And so Hn has satisfies a sort of truncated version of this. But since these are unitriangular matrices and these are non-zero, this implies that determinant of Hn is not equal to 0. So that one way is easy. For the other way, we will construct an OPS with respect to, and then use Favard's theorem. We will construct an OPS with respect to L of x to the n equals Bn. So we will actually write down explicitly the thing. So what you do is define Pnx. This is a very clever construction to be determinant of space here. Determinant B0, B1, Pn, and we'll go up to the last but one row, and in the last row we will put 1 x to the power. So this has n plus 1 column, and then we will divide by determinant of Hn minus 1. So you define this polynomial Pn, then certainly Pn has degree n, and it is also monic because if you look at the coefficient of x to the n, it is precisely this determinant Hn minus 1, this submatrix here. So and now all we need to do is we need to check that it is an orthogonal polynomial sequence. So L of, we'll use the second criterion which I had proved. Let's compute this. So what will happen if you do this? Then what you're doing is basically x to the k will become bk. X no. So if you wanted to just compute L of this, then you would replace x by uh, uh, x to the power k by bk. But now we are multiplying by x to the power k. So here we will get x to the power k, x to the power k plus 1 up to x to the power k plus n. So what we will get is that this is determinant of b0 up to bn n minus 1 to b2n minus 1. And then in the last row, we will get bk up to bk plus n. This is what divided by determinant of hn minus 1. Okay, so I've just replaced.
Sorry. What did you do the last one? So x to the k, if you replace it by b sub k,
No, so there's also a multiplication by x to the power k on the left hand side. So,
Yeah.
so this will become x to the power k.
Yeah.
This will become x to the power k plus 1.
Yeah.
And this will become x. So I have replaced them by bk up to b to the k plus 1.
I am lost. Why can you do that?
Because L of x to the power whatever is the corresponding b. So it's this into some determinant, this into some.
Got it.
So that's it. And so this is so nice now because you can immediately see that if k is less than n, then this last row here will coincide with some earlier row. Because last row equals kth row. So the determinant will vanish and it is equal to delta determinant hn divided by determinant hn minus 1 if k equals n. So it's an OPS with respect to so Pn x is an OPS with respect to determinant hn lxn. So in particular, what you get is very interesting that this has to be equal to vk. So you also compute the ratio of the Hankel, therefore the Hankel determinant. And there's a very beautiful proof of this using the LGB lemma for the Hankel determinants. That's was done by Xavier in his um, course, because this is a matrix whose entries are paths uh, uh, from somewhere to somewhere. These kind of uh, um, they, they're Motzkin prefix Motzkin paths from somewhere to somewhere. And so you have to set it up, but what you will find is that the non-crossing paths will only leave these weights. So this has a nice proof using LGB. This identity has a nice proof. But here I think we are seeing it just from Favard's theorem. Okay, wait. Are we seeing it with respect to? Okay. This needs to be proved, right? Our proof here is contingent upon this identity.
No, wait a second. What did you want to prove? 1 second. We wanted to show that it was an OPS, right?
Yeah.
And what is the condition for an OPS? It is some lambda n delta mn.
So I wanted to show that if the determinant of Hn is non-zero, then Bn is a Catalan sequence. I guess that's fine. That's fine. There's no problem there.
Bn is a Catalan sequence.
Oh, no, maybe it's not so clear. So I want to show that Bn is a Catalan sequence. So what I'll do is I will show that there exists a system of orthogonal polynomials which with moments given by the Bn's. So that's what I want to show. But what I've constructed is a system of orthogonal polynomials with moments given by these ratios of determinants.
Yeah.
So I need to know that these are equal.
No, but doesn't that follow from, if you construct them, these are the moments. So the
What else do I know about these polynomials?
No, I mean, see, previously you had this, first theorem where I'm a little confused. So if you had this AH, whatever,
Yeah,
this factorization, etc., then
yeah.
the Hankel matrices, the entries of the Hankel matrix, the first row is the first column of the A, right?
Oh, okay, okay, okay. I see what you're saying. Yeah. No, but why should HN admit factorization?
That's right. Theorem,
So
theorem is
suppose
that
determinant HN is non-zero for all, and that's all we know right now.
but then you have shown that there is.
We have shown that there is an orthogonal polynomial sequence with moments given by determinant Hn by determinant Hn minus 1.
Uh-huh. And then therefore there is an A and so on, right?
Yeah, but what are the Catalan sequences of that A? It has to be the same as.
Yeah, I guess I get it. Yeah.
Yeah. So this is
Yeah.
yeah. So this
This is
needs.
required.
Yeah,
Yeah.
yeah, yeah. So yeah. So this has a nice proof using LGVM. So I guess yeah, if I'm not mistaken, we need this as well.
So you're saying this is needed. This LG
Yeah,
lemma proof
yeah,
is actually needed.
yeah. That's what it seems like.